Guys, my name is Jung Sing. Okay, as an introduction to our experiment, we are doing the vibration of 2 degrees of freedom, and it's a force vibration. So, being a 2 degrees of freedom, we have two mass, which is mass 1 here and mass 2. So, as for the first objective, we are going to determine the effect of varying speed towards the natural frequency of this system. You can see the speed starts slow, so by varying speed, we vary the speed. So, as the speed increases, and as the force will increase as well. So as the force increase, the vibration will increase as well. Okay, this is the effect of varying speed towards the natural frequency. And next, I would like to continue with the second objective, with the increasing mass effect towards the natural frequency. In increasing mass, we fix mass 2 as 0.95 Newton, as we alter the mass 1 from 0.94 Newton, 0.094 Newton until 10.94 Newton. So as the mass increase, the theoretical value is our natural frequency will increase as well. Last but not least, our final objective will be to compare the natural frequency obtained using theoretical method and the natural frequency obtained using experiment method. That's all for me. Thank you.
Assalamualaikum. My name is Nadia Atika and I will proceed about the equipment and tools. Okay, for the 2 degree of freedom vibration testing, we use stainless steel bead with 1082.5 gram motor and drive load, rotating disc, load, tachometer, measuring tape, accelerometer, motor operating unit, data acquisition system, motor, monitor, and software. Software we use with NIDAQ and deviation. Then we continue with varying speed. Okay, XRTS is used as the speed we apply force on mass 2. The mass 2 is constant as 9.5 Newton, and these two masses are constant throughout the experiment. Okay, the system is left to vibrate by turning on the power source. The result obtained are tabulated and analyzed using deviation. The calculations are done using appropriate parameters set in experiment, mass and RPM. Okay, step 1 to step 5 is continue until we get the result. We continue with the varying mass. The XM mass is used as mass 1. We use 0.94, 1.94 and 2.94 until 10.94 Newton as a mass 1 and 9.5 Newton as a mass 2. Okay, the speed is set as 8 RPS and is constant throughout the experiment. Okay, the system is left to vibrate by turning on the motor. The result obtained are tabulated and analyzed using deviation. The calculations are done using the parameters set, mass, RPM. Okay, step 1 to 5 are repeated using XN as a mass. I will proceed with deviation. Okay, for input, we select the file name 2DOF. We use scaling to convert from G to meter per second squared. We use the digital filter with the low pass 15 and the high pass 10. Then its mean the limit is from 10 to 15. Okay, then we use the FFT to convert the time domain to frequency domain. Okay, it is from meter per second to hertz. Okay, then after finish the setup connection, click measurement at toolbar, choose the hardware, set up NIDAQ, then synchronize it, and finally click run and start to record the reading. Tune the motor speed to state the maximum beam deflection, record the frequency, and tune the speed to the state of minimum beam deflection, record the frequency, and the deviation is run to get other reading. Okay, that's all from me. Thank you.
Hi, my name is William. I will talk to you about how we obtain the results.
So we can see that there are two accelerometers. So we call this mass 1 at this point and mass 2 at this point. In this condition, it is actually unloaded. I will vary the motor speed how the graph will change. Achieving our second objective, we will set the speed at a constant, which is about 8 Hz. And then for mass 2, we will also set it constant, means that we will not be adding any weight at position 2. While for mass 1, we will add 100 gram weight to it. And then we'll see how the natural frequency changes. Right, ready? These two graphs show the result of the experiment. In this structure, the beam is divided into two portions, with the first portion measured 40 cm, the second portion 35 cm. These are mass 1 and mass 2. This is the spring with spring constant K1. The first portion of beam having a spring constant K2, and the second portion having spring constant K3. Last but not least, this is a force vibration system having a rotating force. This is a schematic diagram that closely approximates the actual system, with two masses and three springs connected as shown. Now on the right hand side is a simplified model of the schematic diagram, which only allows the masses to move in the vertical direction. So here are some assumptions. The beam is massless, the beam is undamped, the system is subjected to harmonic excitation, and the gravity force G equals to 10 meters per second squared. To find the equations of motion, we first draw the free body diagram for mass 1. By applying the equation of static equilibrium, we obtain the equation of motion for mass 1. Using the same step, we obtain the equation of motion for mass 2. This is the equation of motion for mass 1 and mass 2 in the matrix form. For natural frequency, let's assume x1 equals to a sine omega t and x2 equals to b sine omega t. By differentiating them twice, we obtain the equations for x double dot 1 and x double dot 2. Then we substitute these equations into equation 1 and equation 2. In harmonic excitation, we assume that sine omega t is not equal to 0. So now take sine omega t equals to 1 and put them back into equations 1 and 2. We finally obtain the characteristic equation in terms of A and B. To find the natural frequencies, we equate the determinant of the matrix to 0. By applying the trivial solution, then by solving the differential equation, we obtain the omega 1 and omega 2. Now let's compare the theoretical natural frequencies to the experimental natural frequencies. In experimental calculation, we obtain omega 1 equals to 67.89 radian per second and omega 2 equals to 174.69 radian per second. While in experiment, we obtain the omega equals to 62.83 radian per second, which is very close to omega 1 obtained from the theory. The reason why we did not obtain the omega 2 from the experiment is because the motor has a maximum rotating speed at about 11 Hz, while in order for us to obtain the omega 2 from the experiment, it will require the motor speed to achieve 28 Hz or higher.
As a conclusion, we have calculated and compared the natural frequency of the system with a different kind of speed. By manipulating speed of the motor from the graph of amplitude versus frequency, we obtained the peak line when resonance occurs. The excitation frequency, it's equivalent to the natural frequency, which is called the omega n. However, there is an error between this theoretical and experimental value. This is because we assume that the mass of the beam is negligible, and we neglect the damping force and assume that gravitational force is equal to 10 meters per second. And for the second objective, we have calculated of the natural frequency of the system with different kind of measures. From this experimental data we obtained, it shows that the acceleration at point 1 increases with increasing mass 1, while acceleration at point 2 decreases when mass 1 increases. However, there is an error between theoretical and experimental value. The error is in the experimental value may be caused by the loss of energy, friction, and also air resistance. That's all from me.